Okay, so first of all, I noticed a typo that I just wanted to bring your attention to. So over here, when I was saying what is the change in the action, I said it should be a surface term. Delta S should have been equal to the integral d4x d mu k mu. So this index mu, I didn't write down on the page. So please make sure you've got the index mu in your notes. Sorry guys for typos. This is inevitable. So please keep watching out and let me know if you've got a question or if you spot a typo. Good. Okay, so let's carry on. What I'd like to do now is I just want to spend a little bit of time talking about the different types of symmetries you can have. And in particular, I want to talk about, first of all, let's talk about discrete symmetries. And to motivate the idea, let's imagine that we have a perfect square. Okay, so this is a perfect square. Again, my figure's not amazing, but that's the perfect square. Now, if I took this square and I rotated by an arbitrary angle, like for example, if I was rotated by 45 degrees, you'd get something that looks like this. And if I said to you, can you tell that I've rotated it? Well, for sure you can tell I've rotated it. So that's not a symmetry. What kinds of rotations could you perform which are a symmetry? Well, first of all, you could rotate it through an angle 0. So if I do a rotation through an angle 0, I don't do anything, and of course nothing has changed. Or I could rotate it through 90 degrees. And if I rotate it through 90 degrees, I'll swap vertical with horizontal sides, and no problem. If you take a look at the figure after rotation or before rotation, they're identical. I could also rotate by an angle pi, which swaps the two vertical sides and the two horizontal sides, but again, it would leave the figure looking completely unchanged. Or we could do a rotation by 3 pi by 2. Anything else that I do, for example, if I do a rotation by 2 pi, well, that leaves the square unchanged. So that's the same as the rotation of naught. If I was to do a rotation through an angle of 5 pi by 2, that would be the same as doing a rotation by pi by 2. So inside this group, the discrete symmetries of the square, there are only 4 different transformations. That's the symmetry group. 4 different transformations, their rotations. But what you can see is the order of this group, the order of the group, that's the number of independent transformations, is just 4. This is the thing that characterizes discrete symmetries. The symmetry group has a finite order. Okay, it's like a set of discrete transformations. Now you might wonder, are there any discrete transformations of relevance for us in physics, particularly in the conformal field theory, which is what we're studying? Well, yes, you've already met one. If you took the group to be the identity element together with inversion, and remember how inversion acted. Inversion took x mu into x mu over x dot x. This was a discrete symmetry. It turns out that this is a group. Why? Well, I squared is just the identity. So you can check that this is a group that satisfies all of the axioms of the group. There are 2 elements in this group. So the order of this group, order of the group is 2. So there's a discrete group that would operate in the CFT. And there may be other discrete groups. If you, for example, look at bosons, then you've got the group of permutations where you permute the particles. That's a symmetry. And for fermions, you've got a Fermi symmetry where if you swap particles, you get a -1. So Bose symmetry and Fermi symmetry would also be examples of discrete symmetry. You can then also have parity, where you would send x into minus x. That would be a parity inversion. Um, that's a discrete symmetry. You could also have time inversion, where you change t into minus t. That's also a discrete transformation. So there are many discrete symmetries that are relevant for physics. What we are more interested in, though, are continuous symmetries. And when we look at continuous symmetries, these are the ones. So what's important about continuous symmetries? Well, they have an infinite order. So there'll be an infinite number of independent transformations in this group. And these are most interesting for us is because these are the ones that Newton's theorem talks about. These imply conservation laws. So you don't get a conservation law for a discrete symmetry. You can have things like selection rules, and we'll be talking about this later. But so discrete symmetries can imply certain restrictions on correlation functions or what transitions can happen between different states, but you don't have a conserved quantity associated with a discrete symmetry. For a continuous symmetry, you do have a conservation law. So what's an example of a continuous symmetry? Well, remember we started talking about the disk that you could rotate by an angle theta. For every distinct value of theta, you get a distinct transformation, and theta can vary between naught and 2 pi. I included naught and not 2 pi because rotating by naught is the same as rotating by 2 pi. I could equally well have done that. Said I'll include the rotation at 2 pi and leave out the rotation at naught. That's a perfectly consistent thing to do, okay, as well. Good. Okay. Now, there's an infinite number of transformations because you can rotate by any angle theta, and two rotations with different thetas are different rotations. There's an infinite number of different transformations in this group. So this is a group of infinite order. And of course, the conformal group itself is an example of a continuous group. In fact, in the conformal group, we've got translations. In exactly the same way that we have a parameter theta to specify rotation, for translation, we've got a continuous parameter a mu. We've also got Lorentz transformations. And for the Lorentz transformations, remember, we had the parameters omega mu nu. Omega was antisymmetric. So let me just remind you of that. So omega mu nu was minus omega nu mu. And these 6 parameters, if you're in 4 dimensions, correspond to angles of rotations and rapidities of boosts. You would also have scaling. So scaling transformations, there's a continuous parameter lambda, and you would also have the special conformal transformations. And the special conformal transformations would have a continuous parameter b nu. Now, you may have heard, I'm not sure if you did, but you may have heard that from translations, the conserved quantity that we get, conserved quantity is the momentum, p mu. From rotations, you may know that the conserved quantity that we get is the angular momentum. Now, I don't know if you know what are the conserved quantity related to the Lorentz boosts. So we're going to talk about that. And then we'll want to find out what are the conserved quantities associated with scalings and with special conformal transformations. And that's what we're going to be doing next. So what do we want to work out? We want to see why these conservation laws arise from continuous symmetries, and we want to find out exactly what is the conserved quantity. We'll be doing that next.